in the diagram at left, I drew it up here above, or I pasted it up here. Line segment AD intersects BE, and line segment AB is parallel to DE. What is the length of side CE? So we want to figure out the length of side. We want to figure out the length of side CE. Now, it might jump out at you, at least it looks like it immediately, that triangle, this small triangle on the left, is going to be similar to this larger triangle on the right. But let's feel good about that. Let's prove that to ourselves. And to help ourselves prove that, we're going to remind ourselves that AB is parallel to DE. And actually, to think about that even more, I'm going to extend these segments a little bit so that you can really start to see that they are parallel lines and that we have a transversal, or we have two transversals that intersect those parallel lines. All right, and I could keep, if I wanted to extend this as a line, I could keep going in both directions. But the bottom line, or not to be punny about it, is that these two things are parallel. That is parallel to that. And that's going to help us establish that these two triangles are similar. Well, the first thing we know is, look, this angle is vertical, is a vertical angle with this angle, so they're going to be congruent. This angle right over here, if you view segment BE as a transversal of the two parallel lines, that right over there is going to be an alternate interior angle. This is going to be an alternate interior angle to this angle right over here. These are alternate interior angles, so they're going to be congruent. If some of this sounds like Greek to you and you are not Greek, and by the same argument, if we look at AD as a transversal, this angle right over here, well, let me do that in a different color. This angle right over here is an alternate interior angle with this one, so they're going to be congruent. But the whole point of everything I just did is to show that, look, the three angles here are congruent to the three angles here, so these must be similar triangles. And the reason why that's useful is because if the two triangles are similar, then the ratio between corresponding sides is going to be the same. So, for example, the ratio of side CE, so we could say the ratio of CE, of the length of segment CE, to say this side right over here. So segment ED, which has length 7.5, is going to be equal to the ratio of the corresponding side to CE. Look, CE is the side opposite this green angle. So if you go on this similar triangle opposite to this green angle, that's segment BC. So it's going to be equal to the ratio of the corresponding side, so 2.1, in the other triangle, to the corresponding side of DE in the other triangle. And this side is opposite this blue angle, this one of the vertical angles right over here. So the corresponding side over here is going to be side BA. So this is going to be over 2.5. So what would CE be equal to? Well, multiple ways to solve this, but one way we could just multiply both sides by 7.5. Multiply both sides by 7.5. Now what's 7.5 divided by 2.5? Well, 75 divided by 25 would be 3. So 7.5 divided by 2.5 is 3. So it's going to be 3. So length of segment CE is 2.1 times 3. So the length of segment CE is going to be, what is that? 6.3. And if we look down here, we see that that is indeed one of the choices.